Daniel Ortiz sat in his cramped Brooklyn living room, the winter light of a late January morning slanting through dusty blinds and casting narrow bands of gray across his workbench. At his fingertips lay the tools of his quiet obsession: a soldering iron warm from hours of use, dozens of resistors and capacitors sorted into small plastic bins, and a half-assembled telemetry module whose bare circuit board was spattered with flux residue. Yet today his focus wasn't on electronics. It was on the glowing screen of his battered laptop, where an email draft awaited his final review. He had spent the past week tailoring his resume for Stewart & Vega Technologies, an industry leader in aerospace control systems. He'd reworked every bullet point, quantified design successes with precise metrics, highlighted his leadership of a university robotics club that built a Mars analog rover, and underscored his self-taught expertise in real-time embedded firmware. He'd even customized the cover letter to reference Stewart & Vega's recent paper on adaptive sensor fusion, citing specific algorithm improvements. Now, at exactly 8:02 a.m., he hovered his cursor over the Send button. He clicked. For a moment, nothing happened. Then the familiar thrum of outgoing mail. He leaned back, exhaled, and waited for the customary acknowledgement. "Thank you for applying." But his inbox stayed silent. He refreshed the page. Nothing. The cursor blinked. A bead of sweat formed at his hairline. 2 minutes later, he opened a new tab to check his home internet connection. No issues. He fired off a test message to his roommate's work account. Test email. FYI, the message sent and was promptly echoed back. Got it. Good connection. So why no response from Stewart & Vega? His phone buzzed with a Slack notification, a teammate at his part-time gig tinkering with drone motors. He dismissed it, eyes glued to the laptop. 10 minutes passed. Still, no automated reply. He opened the company's careers page to confirm the application window. Position open until January 31st. Review process begins immediately. He blinked. He was already late. At 8:20, panic set in. His heart thudded as he dialed the recruiter's direct line. No answer. Voicemail full. He scoured LinkedIn for a hiring manager contact. Every profile he found required pressing Connect and an ambiguous one-sentence introduction. Frustrated, he tapped out a follow-up email. Dear Stewart & Vega recruitment team, I submitted my application earlier today for the embedded systems engineer role and wanted to ensure it was received. He hit send, but again, no confirmation ping. By lunchtime, resignation had set in. A terse rejection landed in his inbox. Thank you for your interest. We will not be moving forward with your candidacy. 2 sentences. No feedback. He stared at those words, dumbfounded. He reread them, searching for hidden praise. Nothing but polite finality. Daniel closed his laptop and stood, pacing the narrow space between his workbench and the fridge. His chest felt heavy, burdened by the weight of unacknowledged nights spent debugging firmware and the countless evenings coaxing printed circuit prototypes to life. Outside, the city carried on, delivery trucks humming along snow-dusted streets, cyclists braving icy lanes, office workers streaming into high-rise lobbies. It all felt absurdly indifferent to his moment of crisis. He paused at the balcony door, peered out at the East River's steel-gray water and the distant Manhattan skyline, and closed his eyes. He recalled the thrill of his side project, the homemade seismic sensors he'd deployed in his parents' backyard to capture aftershock tremors, the code that uploaded data to a web portal he built from scratch, the small bookstores that had retweeted his open-source design to earthquake response teams. No HR recruiter had cared. Yet in those unpublicized experiments lay the spark that kept him awake at midnight. Daniel returned to the workbench, ran a hand across the disassembled telemetry module, and felt resolve replace frustration. His worth would not be defined by rejection emails or corporate gatekeepers. If Stewart & Vega wouldn't give him a chance, he would create one for himself, leveraging the same raw skills the world had overlooked. He picked up the soldering iron, its tip still hot, and set it to the board's edge. As the first bead of solder melted into place, Daniel knew that this was merely the beginning of a journey none of the recruiters could derail. That evening, long after the rejection email had faded into his archive, Daniel returned to his makeshift workshop, a folding table crammed into the corner of his studio apartment where stray circuit boards mingled with takeout containers and engineering textbooks. He booted up his soldering iron, the tip glowing orange hot as he retrieved a fresh spool of 0.02-inch solder wire. On the table lay the heart of his side project, a custom-designed telemetry board populated with a 32-bit ARM microcontroller, a precision 24-bit analog-to-digital converter, and an array of 3 piezoelectric MEMS accelerometers harvested from discarded smartphones. His plan was ambitious. Deploy a network of these units across a seismically active zone in upstate New York to capture real-time aftershock data and stream it to an online dashboard for first responders. The first step was final assembly and calibration. With practiced hands, Daniel aligned the microcontroller on its footprint, applied flux, and inched the soldering iron along the pins, twisting each joint into a neat fillet. Next, he soldered the ADC chip, ensuring its thermal pad connected rigidly to the underlying ground plane for optimal noise performance. Finally, he affixed the accelerometers at precise 120-degree offsets on a separate daughter board, their orientation critical for accurately resolving motion vectors in 3 dimensions. Once the hardware was assembled, Daniel turned to power conditioning. He wired a low-noise LDO regulator to step the apartment's erratic 12V adapter down to a stable 3.3V rail, then filtered it through a PI network of ceramic and tantalum capacitors to isolate the sensitive ADC inputs. He clipped in a rechargeable LiPo cell, hand-wrapped in Kapton tape for insulation, and added a miniature fuel gauge IC wired to an I2C bus. A quick loop to the microcontroller's firmware allowed the board to report battery voltage and state of charge alongside seismic data. With the hardware complete, Daniel slid into his chair and opened his IDE. He navigated to the data acquisition routine where a timer interrupt triggered ADC sampling at 1000 Hz per axis. He adjusted the decimation filter parameters to balance resolution and throughput, then added routines to package time-stamped readings into 64-byte UDP packets. After a few keystrokes, he compiled the code, loaded it onto the board via a JTAG programmer, and reset the unit. The LED indicator flickered to life. Solid green for power, then a rhythmic blue blink marking successful network association with his home Wi-Fi. He opened a terminal window on his laptop and typed NC LU 5005 to listen for incoming packets. A moment later, he saw a stream of comma-separated values, 3 signed integers per sample, followed by millisecond timestamps, raw data flowing from the sensor as it captured the subtle vibrations of his apartment's creaking pipes. Elated, Daniel scripted a Python parser to convert the UDP feed into a live plot, installing matplotlib on his system. As the board sat quietly on the table, the real-time graph showed a gentle noise floor punctuated by spikes whenever he tapped the desk. He gently drummed his fingertips on the table surface, producing a predictable waveform whose amplitude and frequency matched expectations. His heart swelled. The board worked. But the true test lay beyond the confines of his apartment. Slipping into his winter coat, Daniel bundled the telemetry unit, a small solar panel for outdoor power, and a roll of zip ties into a messenger bag. He hopped on his battered bicycle and pedaled 2 hours north to a friend's farmhouse on the edge of the Taconic Range, a location chosen for its history of low-magnitude aftershocks. At the farmhouse's weathered barn, he mounted the board inside a waterproof enclosure, aligning the accelerometer axes to true north using a cheap handheld compass. He secured the solar panel on the barn's south-facing wall, tethering its output into a charge controller that fed both the LiPo cell and a backup lead-acid battery. He configured the board's network settings to use a cellular broadband modem, an IoT data SIM he had purchased for remote deployments. With everything in place, Daniel powered up the system. The LED flickered through its sequence, then settled into its heartbeat blink. A quick terminal session on his laptop confirmed that data packets were streaming over the cellular link to his cloud server. He navigated to his web dashboard and saw the first telemetry values plotted as a flat line, ambient vibrations well within safe thresholds. Satisfied, Daniel packed his gear and rode back to Brooklyn under a sky full of stars. In his mind raced plans for scaling. Mesh networking multiple nodes, integrating temperature and humidity sensors, and collaborating with geophysicists to interpret the data. His phone buzzed with a friend's text. "Website live, looks amazing." He smiled, imagining how, in the near future, emergency teams would rely on his grassroots sensor network to respond faster after an earthquake. Back at his apartment, he dropped the now empty enclosure on his workbench and stared at the half-assembled drone frame waiting for repair. Stewart and Vega's rejection now felt distant. His side project, once a hobby, had proven its viability under real-world conditions. Daniel opened his inbox out of habit. Among the spam and newsletters, he saw a new email from a government research grant program he'd applied to months ago. The subject line read, "Funding decision, approved." As he pumped his fist in the air, the telemetry data continued streaming in. From the barn, its relentless pulse a testament to his perseverance and a clear signal that his work, not a corporate resume, would define his impact on the world. Deep beneath the afternoon sky, Daniel stared at the live dashboard on his laptop, watching the telemetry curves ripple across the screen. Each tremor of the farmhouse's foundations, every distant rumble from passing trucks on the country road, registered as delicate sine waves, their gentle oscillations dancing through the real-time plot. For weeks, the sensors had dutifully recorded ambient vibrations, boiler thumps, wind gusts rattling the barn siding, the distant hum of agricultural machinery. But today, as he sipped lukewarm coffee and peered at the data, he noticed something different. A crisp spike that soared well above the noise floor and then receded in a smooth, exponential decay. Exactly the signature of an aftershock event he had hoped to capture. His pulse quickened. He zoomed in on the timestamp, 3-digit precision showing the exact millisecond of the peak. Outside, the winter air felt charged, as if echoing the seismic energy beneath the Earth's crust. Daniel tapped the export button, saving a high-resolution CSV of the last 20 seconds of data, then switched over to his integrated mapping interface. He plotted the sensor location on a topographic map and overlaid the seismic trace on regional fault line contours. The epicenter, extrapolated from the single node's decay curve and his own empirical calibration, lay less than 10 kilometers away, on the very edge of the tectonic thrust belt. A thrill of discovery coursed through him. This was not simulated noise. This was real Earth movement. A quake too small to register on national seismographs, too remote to warrant a station of its own, but precisely the kind of micro-event that could presage larger ruptures. Daniel opened his terminal and initiated an automated report. Raw waveform data attached, location coordinates, timestamp, sensor health metrics, battery state, all encoded into a secure JSON packet ready for dispatch. He hit send, and within seconds, his cloud server acknowledged receipt and forwarded the alert to his private Slack channel. Moments later, 3 pings lit up his screen, messages from fellow volunteers in his emergent sensor network. One by one, they confirmed they had seen the anomaly too, from adjacent nodes placed in neighbors' barns. The coordinated confirmation validated the initial reading and enabled precise triangulation. The microquake's epicenter now fixed with far greater accuracy than any single station could achieve. Daniel grinned as he began drafting a white paper summary, citing the raw data alongside comparative measurements from the USGS feed, which showed no record of the event. This was proof that his low-cost, grassroots array could fill gaps in the National Seismic Monitoring Network. By evening, Daniel had assembled the results into a coherent narrative, a brief introduction to the limitations of existing monitoring, a methods section detailing his open-source hardware and firmware, followed by a detailed case study of this. Microquake capture. He uploaded a draft to a preprint server and tagged several academic collaborators he had quietly recruited, geophysics graduate students hungry for real-world data. Within an hour, 2 of them had responded with enthusiastic feedback and requests for raw logs, and one offered to run his own cross-validation analysis using regional accelerometer arrays. In the days that followed, the story spread beyond academic circles. A local news outlet picked up the preprint and ran an article under the headline, "Brooklyn Engineer Tracks Quake Too Small for Government Sensors." The piece quoted Daniel on the importance of hyper-local data for earthquake preparedness and featured a photograph of his barn-mounted sensor box perched beside a weathered milking station. His inbox flooded with inquiries. A state emergency management office wanted to pilot 10 more units along a vulnerable stretch of the Appalachian Fault. An environmental monitoring nonprofit requested a technology transfer meeting. Even a major scientific equipment manufacturer asked to discuss licensing possibilities. As notification emails stacked up, Daniel found himself at a crossroads. His side project, once a solitary experiment born of personal curiosity, had become indispensable to professionals in seismology and disaster response. He realized that to meet demand and to ensure open access, he would need to formalize his design under patent protection and mass-produce calibrated units. The patent process promised institutional safeguards and the capital to scale, but it also risked closing off the open-source ethos that fueled community innovation. Leaning back in his chair, Daniel reflected on how a single fleeting tremor, captured at 3 minutes past dawn, had transformed his hobby into a tool of real-time discovery. He opened a new document, ready to draft the patent claims: precise circuit topologies, unique firmware algorithms for onboard event detection, and the novel low-power mesh network architecture that enabled accurate triangulation. His hands trembled slightly with the weight of the moment. A side project born in rejection was on the cusp of becoming the world's most valuable patent in seismic monitoring, one that might save lives by giving communities precious seconds of warning before the ground shook beneath them. By mid-morning, Daniel's small apartment had transformed into a makeshift patent lab. His workbench, already strewn with circuit boards, soldering tools, and half-written code, now supported stacks of technical reference books, the latest USPTO guidelines, wikis on patent drafting, and a thick, dog-eared treatise on intellectual property in electronics. He sat hunched over his laptop, the glare of the screen reflecting his frenzied notes. Fig. 5. Low-noise analog front end. Claim 12. Real-time waveform edge detection. Section 3.2. Peer-to-peer mesh communication protocol. At 9:30 a.m., his phone rang. It was Ellen Park, the patent attorney he had consulted last week, a brisk, sharp-minded former engineer turned IP specialist. Daniel shuffled through a pile of printouts and motioned for her to join the video call. Ellen's face appeared in a split second, her office shelves lined with legal tomes and framed patents awarded to her clients. "Daniel," she began, voice both warm and businesslike, "I've reviewed your draft claims. They're promising, but we need to tighten the language around the event-triggered firmware loop and the node synchronization handshake. USPTO examiners will look for specific novelty over prior accelerometer patents and IoT mesh architectures." She tapped a pen against her chin. "Let's walk through your core innovations one by one." Daniel shared his screen, displaying a schematic of the telemetry node's PCB layout. "First," he said, pointing to the analog front-end section, "we have a matched impedance input stage that reduces thermal noise by 50% compared to standard designs. That enables lower detection thresholds for microseismic events." Ellen annotated the diagram with her stylus, circling key components. "Good. In your claims, you'll want to refer to a matched impedance differential amplifier stage configured to maintain sub-2 UV Hertz input referred noise. Be specific about the component values. Mention the 10 kΩ resistor network you used and the 0.1% tolerance. That technical precision strengthens your novelty. Daniel nodded, typing the exact resistor specs into his draft. Ellen continued. Next, the firmware algorithm. Your adaptive thresholding routine, that's unique because it calculates windowed standard deviation of real-time samples and adjusts the trigger threshold dynamically. Can you summarize that? He opened the code snippet on his IDE. Sure. The ISR computes standard deviation over the last 256 samples every 10 MFs, then sets the event threshold to 2 times the rolling sigma. That allows the node to differentiate genuine seismic spikes from environmental noise. Excellent, Ellen said, marking her notes. In the patent, describe it as an interrupt-driven adaptive thresholding module that computes rolling statistical variance to dynamically adjust event detection sensitivity. Notice the legal phrasing, module, and computes. They moved to the mesh network protocol. Daniel displayed the network diagram, nodes linked by low-power sub-GHz radios forming a self-healing grid. Our protocol broadcasts a time-stamped sync packet every second. Neighbors respond with echo packets, allowing each node to triangulate its neighbor's clock offsets with microsecond precision. Ellen's eyebrows rose. That's compelling. Frame it as a peer synchronization handshake, using broadcast echo packets to establish precise time alignment across network nodes without centralized master clocks. And we need to cite Nakamoto's mesh protocols to distinguish your echo timing approach. They spent the next hour refining 20 patent claims, each claim meticulously cross-referenced to figures in his patent drawings, top-view PCB layouts, firmware flowcharts, network sequence diagrams. Ellen reminded Daniel to include dependent claims, for example, the telemetry apparatus of Claim 1, wherein the firmware further implements a power-saving sleep cycle between sampling intervals. These fallback claims, she explained, preserve his IP, breadth even if some primary claims are challenged. By noon, they reviewed the patent application's abstract. A low-power seismic telemetry node comprising a matched impedance analog front end, an adaptive thresholding module, and a peer-to-peer synchronization protocol, enabling real-time detection and triangulation of microseismic events in distributed sensor networks. Ellen smiled and nodded. That captures your invention concisely. They finalized the drawings, exploded views of the PCB, timing diagrams of the firmware, and flowcharts of the mesh handshake process, each annotated with reference numerals matching the claim language. Daniel uploaded the polished PDF to Ellen's secure portal. She confirmed receipt and scheduled the filing for the following week, assuring him they would monitor the examiner's feedback and prepare any necessary responses to office actions. As the call ended, Daniel stretched, relief and exhilaration washing over him. The legal scaffolding was in place, a robust, precise patent application that would protect his innovations and pave the way for investment and manufacturing. He glanced at his workbench's telemetry node prototype, its LED heartbeat pulsing. In weeks, it would be safeguarded in the patent registry, transforming his side project from obscurity to protected property and setting the stage for the world's most valuable patent in seismic monitoring. By the following Monday, Daniel's inbox was overflowing with meeting requests and partnership inquiries. He started the day at 8 a.m. with a video conference alongside representatives from the New York State Office of Emergency Management. On screen, the state's chief seismologist, Dr. Laura Chen, peered over thick-rimmed glasses. Daniel, Dr. Chen began, voice clipped with urgency. Your microquake detection nodes have demonstrated unprecedented sensitivity. We'd like to deploy 30 units across the lower Hudson Valley for a 6-month pilot. She shared a map dotted with strategic locations, schools, bridges, and electrical substations, all critical infrastructure points awaiting real-time tremor alerts. Daniel clicked through his deployment plan. 15 minutes per installation, remote configuration via over-the-air updates, battery solar hybrid power systems for uninterrupted operation, and secure MQTT channels feeding data into the state's incident response dashboard. He detailed the maintenance schedule, quarterly firmware health checks, and annual hardware inspections, and the hardware supply chain, 100 units ready to ship within 8 weeks from his small contract manufacturer in upstate New York. By midday, he was in Midtown at a polished conference suite with executives from TremorTech Inc., a leading provider of industrial monitoring solutions. They crowded around his demonstration setup, a sleek enclosure housing his telemetry node connected to a miniature shake table programmed to simulate a 3.2 magnitude aftershock. As the table rattled, the live plot on a large monitor registered the precise waveform, triggering automated alert messages that popped up on their company tablets. The TremorTech VP of Product, James Albright, leaned forward. "We can integrate your sensors with our existing structural health monitoring platforms. Our clients, energy utilities and high-rise developers, will pay top dollar for this accuracy. Let's discuss a licensing agreement." He slid a non-disclosure form and term sheet across the table. Daniel examined the term sheet, a tiered royalty model starting at 5% of gross sales, with volume discounts kicking in at 1,000 units per quarter, plus an upfront license fee of $250,000. He had expected aggressive offers, but this struck a balance between immediate funding and future revenue. He requested a 90-day exclusivity window to finalize the state pilot before committing. TremorTech's lawyers agreed to the timeline, noting the potential for co-branded sensor dashboard bundles. That afternoon, Daniel convened a video call with his manufacturing partner in Rochester. On screen, factory floor supervisors hovered over injection molding machines printing new enclosures in industrial nylon. He reviewed the first production batch's quality assurance reports. Tolerances within plus 0.11 mim, waterproof seals passing IP67 tests, and EMI shielding layers meeting Class B compliance. They scheduled a production run of 200 units for the state pilot and 500 units for TremorTech's initial order, with an option to scale to 5,000 units per month. As evening settled, Daniel returned to his apartment to review the day's revenue projections. He drafted formal responses, acceptance of the NYOEM pilot, negotiation points on the licensing term sheet, and a revised supply agreement proposal setting lead times and price breaks for higher volumes. He prepared an equity term sheet for a potential angel investor who wanted in on the ground floor, offering 10% of his newly formed startup, SeismoSense Inc., in exchange for $500,000 of growth capital. Finally, Daniel paused to reflect. In just 5 days, his side project had moved from a patented concept to orchestrated government deployments, enterprise licensing, and large-scale manufacturing. The telemetry nodes, once rejected by corporate HR, were now positioned to become the backbone of a global microseismic monitoring network. As he sent off the last email at midnight, the data dashboard on his second monitor continued to stream fresh tremor readings from upstate New York, a steady reminder that his invention was already at work, quietly safeguarding critical infrastructure, and illustrating how perseverance and technical rigor could turn a side project into the world's most valuable patent. By the time winter thawed into early spring, SeismoSense Inc. had transformed from a one-man garage operation into a company with 50 employees, a fully leased office space in downtown Albany, and a rapidly growing roster of high-profile clients. On March 14th, Daniel Ortiz arrived at the Rochester Manufacturing Park facility before dawn, greeted by the hum of injection molding machines and the steady rhythm of assembly line stations. Today marked the kickoff of a major global rollout, the first tranche of 5,000 telemetry nodes, headed for earthquake-prone regions from California to Japan. Inside the quality control lab, Daniel oversaw a final 100-unit batch undergoing rigorous stress testing. Each node was subjected to a 5G shock pulse on the vibration table, a waterproof submersion test at 2 meters for 30 minutes, and a 3-hour continuous run test verifying battery and radio performance. Engineers in white coats monitored oscilloscope traces and thermal logs, comparing each unit's performance to the acceptance criteria established in Daniel's original patent. A green pass light illuminated on the last tester, triggering a round of quiet applause. Daniel allowed himself a small, triumphant smile. Every time-stamped log and sealed weld was a testament to months of unrelenting refinement. That afternoon, Daniel boarded a charter flight bound for San Francisco, where SeismoSense had secured a strategic partnership with the California Geological Survey. In the sleek eaves of the State Geology Building, he joined the director, Dr. Maria Vasquez, and her team of field geologists to install 200 nodes along the Hayward Fault's urban corridor. Daniel placed the first unit at the base of an aged bridge abutment, securing its solar panel and confirming cellular connectivity via his tablet. As the node's LED heartbeat pulsed, Dr. Vasquez pressed her hand to its enclosure. "This will change how fast we alert communities," she said, eyes bright with anticipation. News of the California deployment hit tech and science media within 24 hours. Headlines proclaimed, "SeismoSense revolutionizes earthquake early warning," and "From Brooklyn basement to global groundbreaking." Daniel found himself fielding requests for keynote appearances at the American Geophysical Union meeting, pitches to national emergency management agencies, and inquiries from international governments desperate to bolster their seismic networks. Back in Albany, SeismoSense's board convened for its quarterly meeting. Daniel presented the latest revenue figures. Licensing deals totaling $12 million, hardware sales at $8 million, and a growing backlog of orders set to push 2025 revenue past $50 million. He outlined a new R&D initiative, integrating environmental sensors for landslide and flood detection, leveraging the same low-power mesh architecture. The board approved a $2 million budget increase for the Innovation Lab and greenlit hiring an additional 10 software and hardware engineers. With scaling well underway, Daniel turned his attention to SeismoSense's public debut. Under the guidance of his CFO, he prepared an S-1 filing for an initial public offering. They chose June 21st, International Day for Disaster Risk Reduction, as the target date, symbolizing their mission to harness technology for community resilience. In the weeks leading up to the IPO, Daniel crisscrossed the country on a whirlwind roadshow, Wall Street investor briefings, broadcast interviews on tech networks, and panel discussions at the World Bank's Disaster Management Forum. He emphasized SeismoSense's proprietary IP, robust manufacturing pipelines, and diverse deployment case studies as proof of sustainable growth. On June 21st, CNBC's opening bell segment featured Daniel standing on the NYSE trading floor, flanked by the ticker display reading SSNS. As he pushed the ceremonial button, shares began trading at $18 apiece, 30% above the initial price range, netting SeismoSense a market valuation of $1.2 billion. Reporters clamored for his reaction. Daniel simply said, "We're building a safer world one tremor at a time," before turning to embrace his team in the gallery. That evening, as city lights flickered on across Manhattan, Daniel stood on his apartment balcony, now upgraded with a view of the Hudson and the city skyline. Below, distant sirens reminded him that hazards never sleep, and above, the soft glow of distant ISP network towers signaled SeismoSense nodes diligently capturing every microtremor. From a resume that had once been dismissed to the helm of a billion-dollar public company, Daniel reflected on how a side project born of rejection had become the world's most valuable patent in seismic monitoring and had redefined how humanity listens to the subtle shifts of the earth beneath its feet. When the World Seismological Congress convened in Geneva that autumn, Daniel Ortiz found himself on the dais of its grand plenary hall just months after his side project had become a publicly traded powerhouse. Delegates from over 100 countries filled the gilded chamber, representing national geological surveys, disaster response agencies, and academic institutions. Behind Daniel, a massive screen displayed a montage. Seismosense nodes, mounted on ancient temples in Nepal, perched on the slopes of Mount Fuji, and lining the ridges of California's fault zone, each one silently feeding tremor data into a unified, global network. Daniel began his keynote with a measured breath. "Distinguished colleagues," he said, voice calm but resonant. 2 years ago, I was writing rejection emails from corporate HR. Today, I stand before you representing a technology that has saved lives by bringing hyperlocal seismic awareness to communities worldwide. He clicked a remote, and the slide shifted to a world map speckled with over 20,000 active nodes, transmitting real-time data. He described how, during a moderate quake in Papua New Guinea last spring, Seismosense's rapid micro-quake alerts triggered automated shutdowns of critical infrastructure, bridges, power grids, and hospital elevators, buying precious seconds for emergency protocols. In Chile, a cluster of nodes had identified foreshocks preceding a major event, allowing coastal towns to evacuate before the main tremor hit. Each case study was accompanied by vivid visuals, dashboards lighting up with tremor waves, control room operators issuing alerts, and residents mobilizing to safe zones. Next, Daniel addressed the patent that had catalyzed this transformation. He acknowledged the rigorous process of securing and defending his intellectual property, but emphasized that Seismosense had deliberately licensed core technology royalty-free to agencies in low-income countries under a humanitarian clause. "Innovation must be accessible," he declared. "No patent, no matter how valuable, should stand between a community and its right to safety." He then unveiled Seismosense's Open Data Initiative, a publicly available API providing anonymized, aggregated seismic readings for researchers, city planners, and citizen scientists. On screen, code snippets and dashboards demonstrated how anyone, from a university geophysics lab to a concerned homeowner, could tap into live tremor data for analysis or app development. "By sharing these insights," he explained, "we accelerate discovery and foster resilience everywhere." As Daniel concluded, the plenary hall rose in a sustained standing ovation. President Amina Kaur of the Global Disaster Risk Reduction Council stepped forward to present him with the inaugural Innovation for Humanity Award, a crystal globe symbolizing Earth's fragility and hope. She praised his journey, from overlooked applicant to architect of the world's most valuable seismic patent, and his unwavering commitment to open access. After the ceremony, journalists and delegates flocked around Daniel. He answered questions on scaling the network to 100,000 nodes, integrating AI-based tremor prediction models, and extending the platform to volcanic activity monitoring. Through it all, he reiterated the lesson of his personal odyssey. Constraints and rejections don't define potential. Ingenuity and persistence do. That evening, Daniel walked the cobblestone streets of Geneva's Old Town, the Congress's banners, still fluttering in the October breeze. He paused at a fountain where children tossed coins, a universal gesture of hope. As he watched them scatter stones into the water's gentle ripples, he reflected on how small actions, be they a tossed coin or a microquake sensor, could produce waves of impact far beyond their origin. Back in his hotel room, he opened a message from a remote village clinic in Nepal. "Your sensor alerted us to tremors beneath the ridge. We evacuated before damage occurred, thank you." Daniel allowed himself a moment of quiet pride, knowing that the technology he'd once cobbled together in a cramped Brooklyn apartment was now woven into the fabric of global safety. He closed his eyes, envisioning the Earth's subtle shifts beneath his feet, and the invisible network of Seismosense nodes listening intently. In that profound silence, Daniel understood that the world's most valuable patent was not measured solely by market capitalization, but by the countless lives it had touched. and the collective resilience it had inspired. As he drifted to sleep, the soft glow of distant city lights below mirrored the vigilant heartbeat of a planet made safer by one man's refusal to be defined by rejection.